let us see that what do we mean by a topological space is a first countable topological space. Let us define, that is a topological capital A topological space capital X comma tau is said to be a first countable topological space, or we just say that is said to be a first countable space if it satisfies the following conditions, namely if for each x in capital X, for each x belongs to capital X, we should get a local base. For each x in X, there exists a local base which is countable. That means there exists a countable local base at X. Then we say that such a topological space is a countable, that is first countable topological space. So, in such a case it is easy to verify the following, namely given that capital X comma tau a first countable topological space. This is given x tau a first countable topological space, and let us fix a x in capital X. Because x is in capital X, the space x tau a first countable topological space, we will get there. So, in this case, hence there exists a countable local base at X. Hence there exists a countable local base at X in capital X, that for that fixed X. So, let us say script beta, this is say U1 comma U2 U3, say script beta because it is a countable collection. So, we write this way, is a countable, is a local base at X. So, now consider a new collection. Now, let say V1 equal to U1, V1 equal to U1, V2 equal to U1 intersection U2 and so on. In general, Vk or Vk for k any positive integer, Vk equal to u1 intersection u2 intersection un. K, here we write K u1 intersection u2 etc. up to intersection uk. K positive integers, then it is easy to see that then this new collection Vn n1 to infinity is again a local base at x and this is countable. Then this is a countable local base at x. I mean proof is almost trivial. That means what we should, if you want to prove that this new collection is a countable local base at x, just start with any u, any open set. See, because these are all local base at x mean already they are all collection of open sets containing the given point x. So, hence this new collection Vn is also a collection of open set containing x. So, now you start with the u any open set containing x. Now, this u suffix n, these are u1 u2 is a countable local base, is a local base at x, implies there exists some n, a natural number n in n such that x belongs to the un which is a subset of the started open set u. Now, x belongs to, we have started with a u open in x, then we got a member un from this collection such that x belongs to un which is contained in x is x is in all the un. Mainly what we want is, that is no need of writing, that is what you want to, x is in un which is contained in u. So, what we have is, now what is our Vn? Vn is n natural numbers, by definition u1 intersection u2 intersection un, which is a subset of un and un is subset of u subset of u. That is, for a given open set u containing x, now we got a member Vn from the new collection satisfying the condition that already x is in Vn which is contained in u. So, hence this new collection is a countable local base at x. So, now we will use this type of local base at x to prove that if our domain, if x is a first countable topological space, x first countable topological space, y is any topological space and f from x to y a function. I mean here we have a topology which is first countable, y any other topological space, then the function f is continuous, that means continuous say at every x, continuous at x in the domain capital X, if and only if it is sequentially continuous. F is, the meaning is whenever xn is a sequence in x, xn converges to x, then fxn converges to fx. So, let us formally state, give the statement. So, this theorem is, that is theorem, let capital X tau be a first countable, be a first countable topological space, and y comma tau prime be a topological space. This need not be first countable, we assume only x is first countable, y tau prime any topological space. Then a function f from x tau to y tau prime is continuous at a point x in x if and only if, this we write for if and only if, whenever xn is a sequence in x, xn converges to x, then fxn should converge to f of x. So, this is if and only if xn in a sequence in xn a sequence in x, we write in short xn a sequence in x, xn converges to x with respect to the given topological space x tau, that implies f of xn converges to f of x. This we are familiar if our spaces are metric spaces. So, here in place of metric space we have a collection of countable, this is a countable collection which is a local base at x. So, we will see that this Vn will take the role of, in a metric space, ball center at, open ball center at x radius 1 by n. So, in fact to prove the first part, namely if I assume that f is continuous at x, whether this, even if the space is not first countable, still the result is true. That is, whenever xn converges to x, then that implies fxn converges to fx. But we need the first countable, the fact that the space is first countable to prove the converse part. So, first part is simple, mean proved. Assume that f x tau, so we have the topology tau on x to y tau prime. Assume that f is a continuous or it is a continuous function, f is continuous. See, then to prove whenever xn is a sequence in x and xn converges to x, then we will have to prove that fxn converges to fx. So, now suppose xn n1 to infinity is a sequence in x so that this point x is fixed. Now, xn is a sequence in x so that xn converges to x, meaning is as n tends to infinity. Now, what is to prove? Let us start from there. Claim or to prove f of xn converges to fx. So, if you want to prove that this fxn converges to fx, by definition start with an open set in y tau prime containing fx. So, let us start now. Take a open set, or let us say V a open set, let capital V be an open set containing fx. So, it is a neighbourhood of fx. Now, our assumption is f is continuous. For any open set containing fx, we will get a open set u containing x such that f of u is subset of x. Now, f from x tau to y tau prime is a continuous function implies there exists an open set, we will write in short, there exists u belongs to tau and it is a open set containing x, there exists u belongs to tau containing x such that f of u is subset of v, is correct. Now, use the fact that xn converges to x. Now, xn converges to x and this xn converges to x. Now, this xn converges to x, u is an open set containing x implies there exists a stage, that means there exists a natural number n naught belongs to n such that xn will belongs to u, xn belongs to u for all n greater than or equal to n naught. Now, consider this, let us call this as 1. Now, xn belongs to u implies f of xn belongs to f of u, but which is subset of v. Hence, from 1 I will write directly, hence from 1 f of xn belongs to f of u which is subset of v, hence this belongs to v when for all n greater than or equal to n naught. So, that is what our definition of f of xn converges to fx. So, start with an open set V containing fx, then we got a stage n naught such that f of xn belongs to V for all n greater than or equal to n naught. This implies f of xn converges to fx. So, this part is relatively easier. Now, the converse part, let us assume that whenever xn is a sequence in x such that xn converges to x, then fxn also converges to fx. So, that part I am not writing. Let us say, see the converse. This part now will fix here, now we will use the fact that our space x is first countable. Now, x is a first countable topological space, just we write space. X is a first countable topological first countable space implies there exists a local base, say v suffix n, n1 to infinity, there exists a local base a v n at x such that satisfying the condition that v suffix n plus 1 is a subset of v n for all natural numbers, for all n belongs to n. Also we have assumed that we have assumed the following, namely, write again in short, xn is a sequence in x, xn converges to x implies fxn should converges to fx. So, then to prove is f is continuous at x. So, now here our aim is to prove the function f is to prove f is continuous at x. Again let us use the fact, somehow we will have to use the given hypothesis, namely if we are able to construct a sequence xn which converges to x, then only we can use the given hypothesis. So, our aim is to construct a sequence. For that, let us assume that this is the negation. See, if a statement P implies Q is equivalent to saying that negation of Q implies negation of P. So, let suppose the given function f is not continuous, suppose f is not continuous at the given point x. So, let us recall what do you mean by continuous at x mean? You start with any open set say W containing f of x, then we should be able to find a open set U containing x such that f of u is a subset of W. So, now this is not true mean instead of for every open set containing fx, now will the negation for all the negation is there exist, hence there will exist. Now, f is not continuous at x imply there exist on open set say W in the codomain y tau prime which will not satisfy the condition that f of u subset of tau u. That means you take any open set u containing x, this condition will not be satisfied. That means this will not be a subset of tau u. There exists an open set tau u in y tau prime satisfying the condition, or we write such that there exists an open set tau u containing the point f x, that is understood. That is, there exists an open set tau u containing f x such that you give any open set u containing x, then f of u will not be a subset of tau u. So, in particular we have this collection V n, they are all open sets containing x. So, this is such that f of V suffix n is not a subset of the given tau u. We have at least one open set tau u containing f x satisfying this condition for all n, for all natural number n belongs to capital N. This means what? Hence there exists, for each n there exists some x n which is in V n, but f of x n is not in tau u. I mean, just we are using the fact that what do you mean by a set is not a subset. So, now we have got x n is in V n. So, now this V n is such that see V 1 superset of V 2 superset V 3 and so on. These are all like the ball center at x radius 1 by n in a metric space sense. So, now this sequence is such that this will converge to x, but f of x n is not in tau u for all n. That means, and tau u is a neighbourhood of or open set containing f x. Hence, we will get a contradiction to our assumption, namely whenever x n converges to x, that imply f x n converges to f x. So, enough to prove x n converges to x as n tends to infinity. So, start with an open set. So, start with an open set, say u containing x. Now, u is a open set containing x and this V n is a local base at x. So, I am not writing all those things. Now u is a open set containing x. Now, I will just write, hence there exists a member from the local base. That means, so we call it n naught belongs to n such that this corresponding V suffix n naught, this x is in V n naught which is contained in our started open set u. That is the definition from the definition of local base at x. See, now what we have taken is x n is in V n. Now, for n greater than or equal to n naught, for n greater than or equal to n naught, because the way we have constructed says V n subset of V n naught, correct, and V n naught is subset of u, and we have taken x n from V n, that is this imply, hence we have x n belongs to we will write that is U V, what is V n naught, which is subset of U started one, not the correct. Yeah, that is, hence we have x n belongs to this U when for all n greater than or equal to n naught. So, that is our definition. From the definition of convergence, we started with an open set containing x, we have got a stage n naught satisfying the condition that x n belongs to U for all n greater than or equal to n naught. That implies x n converges to x, but f x n is not in tau u, which is a neighbourhood of f x. So, this gives a contradiction to our assumption, namely x n converges to x imply f x n converges to f x. We arrived at this contradiction by assuming that f is not continuous at x, hence that assumption is wrong. Therefore, f is a continuous function at x and x is arbitrary, hence f is continuous. Yeah, this, and in fact the similar concept which we call it second countable, see, like first countable is in some sense local, for each point we have a countable local base at x. A space x is said to be, space means for us topological space, a topological space x tau is said to be a second countable, is said to be a second countable topological space. We just write said to be a second countable topological space if it has a countable base, if it has a countable base, and it is easy to prove that every second countable topological space is first countable. For example, all this familiar topological space comes from the metric. See, like R set of real numbers with usual topology induced by the usual metric. So, this is second countable. So, it is second countable. In fact, we can take all the open interval, open a comma open b, such that a comma b belongs to Q, the set of rational. Yeah, then this is a countable set. This collection is our, this is a countable base for R, hence R is second countable. Similarly, we can prove that in R power n is second countable. In fact, we have seen there are some function spaces which has this nice property. So, in particular Rn mean set of all x1, x2, xn, so that each xi belongs to R, I varies from 1 to n. These are all second countable topological spaces. Now, we will give you a simple example. See, if we take x is any uncountable set, x uncountable set, tau suffix capital D. So, let us say the discrete topology on x. What is the discrete topology on x mean? The power set of x. every set is open. So, this is our topology. Here this topological space cannot have a countable base, because even the singleton x, x in x, this collection is uncountable. And if you start any base, then singleton x is open. Hence, for this open set singleton x, there should exist a member from here, say b suffix x containing x and contained in this. So, that means all those things that containing x already contained in singleton x, that means that such a open set should be singleton x. So, this any discrete beta which is a base for this mean this will contain this uncountable set. So, it cannot have a countable base, that means it is not second countable, whereas it will be, it is first countable. So, other non-trivial example is what we call, again we will not explain everything, L infinity. This will come across in analysis classes. I mean each element itself a sequence. Set of all xn, xn is a sequence and it is a special type of sequence which we call it say bounded sequence of real numbers. Even if we take complex number it will do, but we will restrict ourselves to say that xn is a bounded sequence. Now, we define the metric d infinity of x mean some xn, y equal to some y suffix n. Then we define supremum of least upper bound mod xn minus yn, n varies over natural number. Then this d suffix infinity is a metric on L infinity. So, that metric will induce a topology. That topological space is not second countable, correct. So, in fact, we can prove that if a topological space is second countable, then it will have a countable base. So, let us quickly state that result. Given x tau a second countable topological space, just we will write second countable, then it will have a countable base. So, let us say that this grid beta B1, B2, Bn dot dot is a countable base. Let us say this is a countable base for our topological space x tau. Yeah, in particular they are all open sets in x tau. Now, without loss of generality, we can assume that each b suffix k, each member is non-empty. So, assume that b suffix n is non-empty for all n. So, now we can take for each n, for each natural number n, let xn belongs to b suffix n, because it is a non-empty set, we can take an element from there. So, I mean just take any one element and fix that we call it xn. I mean that means we are constructing a new set, in some sense it is by axiom of choice. So, let that is now let that means by axiom of choice we construct a new set xn or x1, x2, x3 say that x1 belongs to B1, in general xn belongs to Bn. Now, this is a countable set. Now, we can now it is easy to prove that, see, claim this closure equal to the whole space X. That means what? This always true, A closure subset of X. So, enough to prove X is subset of A closure. So, that means take an element X in X, we have to prove that X is in A closure. That means you have to start with a open set U containing X. Now, U is a open set containing X and this collection script beta a basis implies X belongs to U, script beta basis for X tau implies there exists a member from here, there exists say B suffix n or there exists n such that this B there exists Bn such that X belongs to Bn contained in U, correct? Yeah. So, this is a open set for each open set U containing X. Now, what we have is this will give us U intersection with A is, so now what is U for each open set U containing X, this U intersection A. Here take Bn belongs to U and Xn belongs to Bn. We have Xn belongs to here, by definition it belongs to Bn which is subset of U. So, Xn belongs to U. Also the way we have constructed Xn is in A, hence we have that Xn will be in, now Xn belongs to this set, that is this implies this set is non-empty for each open set U containing X, U intersection A is non-empty, that implies X is in A closure. That means we have proved if we take X in X then that is subset of A closure, because this is the whole space, this implies A closure equal to capital X. So, we got a countable subset A of capital X such that the closure is the whole space. Such a topological space we call it a separable topological space. So, hence what we have proved is every second countable topological space is a separable topological space. In fact, in a metric space the other way separable imply, if a metric space is separable it is also second countable, but in a topological space this result is not true, will not have sufficient time to see the proof, just will state the result. I mean we have seen that R with the lower limit topology, that is what is a base is set of all closed A open B such that A comma B belongs to R A less than B. So, in fact this is a the topology generated by this base, this is a base for some topology on R, that topology is called lower limit topology, this we have seen many times, and this topological space is separable. We can take all the rationals and we can prove that that closure equal to R. So, then R suffix L is separable, but R L meaning is the R with this topology, the topology generated by tau, this we call it tau suffix beta suffix L, let us just call it tau L. With respect to that topological space, RL is separable but not second countable, but RL is not second countable. So, this brings the, I mean these are all the difference between a topological space and a metric space. Not all the results which are true in a metric space will be true in a topological space. So, and also we can see we started with that L infinity and we can prove that the L infinity is not even separable. So, just I will quote again it is easy to, I mean again we have included this result in our notes, namely if a metric space is separable, then every subspace is also separable. X separable, Y subspace of X, that means the metric is restricted to Y, imply Y is separable. In short, we say that subspace of a separable metric space is separable, but in a topological space that need not be true. Can give example of a topological space which is separable, but yes, yeah, subspace need not be separable. So, here we can consider the subspace, in fact we call, so let us say the subspace A Y in L infinity, the set of all bounded sequences of real numbers. Here we take capital Y because we want that each element in Y should be in L infinity, they are all bounded sequences. The very simple bounded sequence is set of all real numbers xn, a sequence of real numbers such that xn belongs to 0 and 1. That means each xn is either 0 or 1. In fact, this is a famous, I mean one of the first example we come across in an analysis course, namely such a set is uncountable, the sequences consisting of zeros and 1. This is uncountable. So, if we take an element x y in capital Y, let x y belongs to capital Y, x not equal to y, then what will happen? X not equal to y imply for at least one n, here x equal to xn, y equal to yn, then for at least one n xn not equal to yn. That means xn if it is 0, yn is 1, or xn is 1 means yn is 0. So, this will imply distance between x comma y equal to 1. So, that means if we restrict our metric to y, here every singleton see if we take a point x, if you consider a ball, center at x, say radius is less than 1, then this will not, if we consider any y here, suppose our radius say half, then distance between y and x should be less than 1. When x not equal to y, it is 1. So, it cannot be less than 1. So, that will contain only the centers singleton x. So, every singleton is a open set. That means, this topology will become discrete. So, we cannot find if A is a countable set, A closer equal to only A, it cannot be the whole space. Hence, this space, this subspace is not separable. So, this gives an for us, hence the original space L infinity is also not separable, because subspace of a separable space is separable. So, as today is the last lecture, we will conclude with this result. Just I want to state that we have prepared a notes for the topology course under NPTEL, and we have included exactly 21 lectures, and we have made it as elementary as possible. In fact, many times we recall the definition and result, so that a beginner who is not attending the regular class will able to follow, and with that aim we have made it a point to repeat or say recall many times already the discussed result in the previous lecture. Whenever we use now even the new result, the related result, either we recall or we define the related concept, and let us hope that some of the student who will read both notes, and before reading the notes it will be nice if they could go through it, go through these video lectures, try to understand the basic concept, then try to read the notes. And of course, like we have mentioned in the very beginning, there are many excellent books are available in topology. After learning the basic concept, one can go for little advanced level, and many times constructing examples are highly non-trivial. Even the first countable topological space, giving an example which is not first countable, it is not all that easier. So, with that remark we will stop, and thank you very much.